Alright, so let's talk about the Aufbau diagrams. You've had period 3's Aufbau diagrams to draw. So it means that the elements have electrons up to the third energy level. So bear with me, because what I want to show you is going to have, it will help you to understand the next few things. So I'm going to do lithiums first. Lithium is in period 2. You didn't have to do lithiums, I'll go away. But I want to do lithiums so that you can see. So lithium has how many electrons? Come, boys and girls, look on your periodic table. How many electrons does lithium atoms have? 3. Because the atomic number is 3, it's got 3 electrons. Are you alright with that? So for lithium, I need 2 energy levels, and in the first energy level we've got a 1s orbital that's got 1 electron in at the start, but Pauli's rule says a maximum of 2 electrons with opposite spin will occupy an orbital. And then we go to the 2s orbital and there will be 1 electron there. Got it? Okay. The 2 p's will be empty. Then we go to sodium. How many electrons does sodium have? We have 11 electrons. And where are these electrons? They're in the first, second and third energy level. And we had to do 1 for, next element is magnesium. Magnesium has 12 electrons. And next element was aluminium, and it's got 13 electrons. And next element is silicon, and it's got 14 electrons. Next element is phosphorus, and it's got 15 electrons. Next element is sulfur, and it's got 16 electrons. Next element is chlorine, and it's got 17 electrons. And next element is argon, and it's got 18 electrons. I'm going to draw them all next to each other so that we can see what they look like. Do I have to draw these energy level lines now? Yes. I'm going to be patient with myself and draw them, and then I'll show you the next thing. Because what is new in this year's section on the periodic table will be the trends in the periodic table. The trends of the elements and their properties. That is what is new. This stuff is not new. You know these things. Okay, so the vertical axis we call the energy, and it's 3, 2, 1. Am I right? Okay, so it's 1s, 2s, 2. I'm going to go for squares. 3 p's. Let's go for squares. Sorry, teacher is becoming more and more lazy. The s orbital and the p orbitals in an energy level is called sublevels. You understand why? They have different energy values, but they're still in the second or the third or the fourth energy level. So they are called sublevels. And we are drawing the electron structure of atoms in their ground state. What does ground state mean? The most, what? The lowest energy state, yes. Are you awake? Now each lot must be labeled 2p, 3s, 3p. I'm just not going to squash it all in there. Okay. Will the green show? So it's 1, 2, Pauli's rule. Maximum of 2 electrons with opposite spin will fill the energy states from the lowest possible energy state. Then we go to whose rule? Hunt's rule. Each p orbital in an energy level will get 1 electron before it can be filled. So that takes us to 10 electrons and one more there for 11. There. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Are you keeping up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What's happening? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Can I skip the others? Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Oh, sorry for my slapdash word here. 1, 2, 3, 4, 5, 6, 7. Oh, come on. Do it better. So in the third energy level, we have what? In the third energy level, we have the s orbital and the 3. Go away. Your brain is damaged. So it's 1, 2, 3, 4, 5. Am I right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, going from lithium to sodium, what happens to the size of the atom? It becomes bigger. So the trend for atomic radius down a group is that the atomic radius increases. So first time ever you hear about atomic radii, more than one radius, down a group increases. Why would it increase? Because every time you move down the group to the next period, you have one more energy level with electrons. Okay, so it's logic. Down a group, the atomic radii increases. Because the number of energy levels increase. Okay. So this is the first trend we are talking about. That one's easy to understand. All right. What happens along a period? Along a period. Before you guess, let me talk you into it. For sodium, you've got 11 protons in the nucleus. How many valence electrons? One valence electron in the third energy level. Magnesium, how many protons do we have in the nucleus? 12 protons. How many valence electrons are there? 2 valence electrons. For aluminium, how many protons are there? 13 protons in the nucleus. How many valence electrons are there? 3 valence electrons. For silicon, how many protons? 14 protons in the nucleus. How many valence electrons? 4 valence electrons. For phosphorus, 15 protons. So, and 5 valence electrons. Sulfur, 16 protons. How many valence electrons? 6 valence electrons. I'm getting there. Be patient. Number 17, chlorine. 17 protons. 7 valence electrons. Argon, 18 protons, 8 valence electrons. Now the big question is, opposite charges have what? Forces of attraction. Listen carefully. The negative charge in the valence energy level is increasing. The positive charge in the nucleus is increasing. What will happen to the strength of the force of attraction between the positive charges in the nucleus and the electrons in the valence energy level? It gets stronger. So I'm going to redraw these things. Let me show you. So these two electrons will be slightly closer to the nucleus, because the force of attraction between the nucleus with one extra proton and another extra electron will be stronger. You getting me? The 3 electrons in the valence energy level will be slightly closer to the 13 protons. The 4 electrons in silicon's valence energy level will be slightly closer to the nucleus. Can we do it the same with all the others? They become closer and closer and closer and closer. So what happens to the size of the atoms when we move along a period? The atomic radii shrinks. The trend is that the atoms become smaller and smaller, because the force of attraction between the valence electrons and the protons becomes stronger. Can I write it down? Okay. Are you still copying something here? Okay. So the trend in the atomic radii along a period. That is from left to right. The atomic radii decreases because the increase in the number of protons in the nuclei and the increase in the number of valence electrons will create stronger forces of attraction, unlike charges attract. Which pulls the electrons closer to the nucleus. Sorry, I haven't been recording this. So, for a sodium ion to form, the valence electron must be lost. For the magnesium ion to form, these valence electrons must be lost. For the aluminium ion to form, the valence electrons must be lost. Because the atom loses electrons to form the cation, the ion is smaller than the neutral atom. Magnesium ions are smaller than magnesium atoms. Aluminium ions are smaller than aluminium atoms. So we say the metal ion have a smaller atomic radii than the metal atoms. Sorry, metal ions have a smaller atomic radii than metal atoms because the valence electrons are given away. Okay, so let's make them disappear again. Sorry for the glitch in my recording. Now what happens on the other side to phosphorus, sulfur and chlorine? They gain electrons. So there's a bigger negative charge, but negative charges tend to repel. Am I right? Yes. So what is going to happen to the non-metal ions? How would the phosphide ion compare to the phosphorus atom? It will be bigger. And the same with the sulfide ion. It will be bigger than the sulfur atom. And the same with the chloride ion. It will be bigger than the chlorine atom. So non-metal ions have bigger radii than the non-metal atoms, because valence electrons are taken in. There will be a bigger repulsion between electrons. Is it making sense? All right, I'll give you a moment to write that down. We've learned from grade 8 that metals are electropositive. And we've learned from grade 8 that non-metals are electronegative. But a metal wants something in exchange for an electron. So the metal is willing to give its electron, usually to a non-metal. But the metal requires payment. You can't go to the tuck shop and buy a Mr. O without giving something in exchange for that sandwich. What we pay with is money. Now, we pay, the atoms pay one another for electrons by giving energy. Are you hearing what I'm saying? So the currency for atoms will be energy. So this sodium atom, when you want to take the electron from it, you need to give it energy. The non-metals, they take the electrons, but it gives off energy. Are you with me? I'm going to write it down now. So, for the neutral sodium to give its electron in a transaction, in order for the sodium to be a cation, it takes in energy. And this energy has a special name. So the sodium takes in, listen to this original name, ionization energy. Okay. So this energy is ionization energy. It's the energy that causes the neutral atom to become a cation. The cation is stable. It's got the electron configuration of the neon atom. Yeah, a metal atom. Yes, to become an ion. Yeah, a cation. Positive ion. Are you with me? Yes? All right. For the chloride atom to take that electron that was given by the sodium in to make the chloride ion, the stable anion, it gives off energy. Don't run ahead. This, what do you call it when you like a girl or you like a boy? There is a kind of love between the two people. What's the English word? Affection? Affection? Are you with me?
Yes.
There's an affinity. Are you following me? There's an affinity. And it's called electron affinity. So the energy that is given off here is not called ionization energy. It is called electron affinity. Yes? Yes.
Electron.
It's the energy that is given off when a non-metal receives electrons. No, it's just I wrote affinity down first because it's the way I'm teaching. And then I put electron, and my spacing was just not right. There's no dash. It's just new chemistry. You never had to think about things like this before. Okay. I want to show you something called a Lewis structure. So a Lewis structure is a way to represent an atom with its valence electrons. And we can use dots or crosses to represent the valence electrons. Because most people draw their dots so small I can't see them, I prefer the cross. But if you write a dot, I'm completely happy as long as I can see there's a dot there. So sodium has a Lewis structure that looks like this, with that little cross representing its valence electron. And that valence electron is given away to make the sodium ion. I think people prefer the dot because it doesn't look like a sideways turned plus. You're welcome to use the dot as long as I can see there's a dot. And the valence electron goes somewhere else. So this is using Lewis structure to show the formation of the ion. Now it looks stupid for sodium, but it will look less stupid for chlorine. How many dots would chlorine atoms have? How many valence electrons does it have? It's got 7 valence electrons. So this time I'm going to group them together like this on the 4 sides of chlorine. And there'll be 1 electron that doesn't have a friend in the p orbital. Okay? If that atom takes in the electron, it becomes the chloride ion with how many valence electrons now? 8 valence electrons, and the negative charge is outside the square bracket. Because the dots and the crosses mean the same thing. They're the valence electrons. So we'll continue from here next time I see you.